In this video, we're going to go over vectors and vector operations. So let's start with something you already know, which are points. In this xy plane, this red point would be 1, 1. Now let's explore what a vector is. This blue arrow is a vector. It has a starting point called the initial point and a ending point called the terminal point. I'm going to label them P0 and P1. To create a vector, we're going to subtract the terminal point by the initial point. You could think of this like component subtraction. We're subtracting the x components and y components separately. There are many ways to symbolize a vector. As you can see here, it can have an arrow on top, angle brackets, a bolder letter, or I and J notation. Let's try this example. It says to find the vector from 2, 3 to 1, 0. First, let's graph the points. We can get the vector graphically by seeing the change in the x and y components. Here the vector is going down 3 and left 1, so the vector will be -1, -3. We can also calculate the vector by subtracting the terminal point by the initial point. And if we do it like this, we also get -1, -3. Vectors also have magnitude and directions. Graphically, the magnitude will be the length of the vector, and the direction will be wherever the vector points. The direction might be an angle with the x-axis or another vector. It'll depend on the context. Let's look at this vector and try to find its magnitude. First, we're going to create a right triangle using the components of the vector. Then we're going to use the Pythagorean theorem and solve for c. This will give us the length. In this example, the components are -1 and -3. And when we put that in, we get square root of 10, which is the length of this vector, also the magnitude. So the magnitude written with absolute value signs around it is equal to the square root of the component squared. Now let's take a look at this vector and try to find its direction with respect with the x-axis. First, we're going to label the x and y components and label the angle as theta. Then to get the angle, we're just going to take the tangent of the angle. After we take the arctan of both sides and put in the values, we're going to get the angle as around 63.4 degrees. Let's look at these two vectors. Notice that their magnitudes, which are their lengths, and their directions are the same. Therefore, we can say that these two vectors are equal to each other. This introduces the concept that vectors can be moved around in space. Let's look at our first vector operation called the vector addition. Let's do it graphically first. To add the two vectors, we're going to bring the initial point of the second vector to the terminal point of the first vector. Then the result will be the vector created by the initial point of the first vector and the end point of the second vector. Here it would be this red vector and it has components 3, 3. You can also do this with component-wise addition. Let's look at our second vector operation, which is scalar multiplication. This is when we multiply a vector by a scalar. If we multiply this blue vector by the scalar 2, then its length will double. Scalar multiplication is also component-wise. It's like we're distributing the 2 to the x and y components. Let's try to multiply this blue vector by the scalar -1. And if we do that, we get this green vector. We notice that it's in the opposite direction of the blue vector. Our last vector operation is subtraction. Let's try to subtract this purple vector by the green vector. What we can do is take the negative of the green vector, then add it to the purple vector. And the result will be our blue vector, which is 2, 0. Vector subtraction is also component-wise. Another way to geometrically subtract vectors is to add the second vector to the initial point of the first vector like this. Then the result will be a vector from the second vector to the first. In this example, we also get the vector 2, 0. Here are the properties of the vector operations we went over so far. You can pause and review these. Now, we're going to look at the unit vector. A unit vector is just a vector with magnitude of 1. If we're trying to find the unit vector of this blue vector, then we're trying to find the vector with magnitude 1 that points in the same direction as shown by this green vector. This vector is 1, 2, so the magnitude will be the square root of 5. Now let's recall scalar multiplication. If we multiply this vector by 2, then the length will be 2 square root of 5. So to get the unit vector, what we have to do is divide the vector by the magnitude of that vector. Then the resulting vector will have a magnitude of 1. This is the formula for the unit vector. Let's look at 3D vectors now. The vector operations for 3D vectors are the same for 2D vectors. The differences between 2D and 3D vectors are their magnitudes and direction. Let's start with their magnitudes. So the magnitude of this vector is given by the equation. And if we put in the components, we're going to get square root of 17. Unlike 2D vectors, where the direction might be with respect to the x-axis, the direction of a 3D vector is just its unit vector. It's also called the directional vector. Recall, to get the unit vector, we just divide by its magnitude. So here the magnitude is square root of 17, and if we divide that out, this is the unit vector we get. Now let's try to get the angles between the vector and the axes. To do this, let's create another vector with components cosine alpha, cosine beta, and cosine epsilon. Now let's set the unit vector we got previously equal to this new vector. And when we solve for the unknowns, the alpha, beta, and epsilon represents the angle between the vector and the axes. In this video, we went over what vectors are, their vector operations, and the unit vector. In the next episode, we're going to explore the dot product, cross product, and triple scalar product.